A rational function is any function formed by the quotient of two polynomials. So if you have a function that has a polynomial in the numerator of a fraction and one in the denominator, we call it a rational function. The basic run-of-the-mill rational function is the graph of 1 over x. If you graph that in your calculator, it's going to look like this. Minus the arrows, but the graph's going to look like this. In this graph, both the x and y axis are considered asymptotes. An asymptote was a line that the graph continuously got closer to but never touched or crossed. Although we're going to find out later on that sometimes part of a graph may cross the horizontal asymptote, but it will never cross a vertical asymptote. So the asymptotes are x equals 0 is the vertical asymptote, which I abbreviate VA, and y equals 0 is a horizontal asymptote, which I abbreviate HA. How about the domain and range of this function? Well, the range is going to be all real numbers. It's basically all real numbers. Except for there's one value that'll never be the output, and that is 0. So the range is all real except y equals 0. The domain is the same thing. It's also all real except x equals 0. And the reason is, if you think about the equation 1 over x and you plug in a 0 in the denominator of a fraction, well, that's undefined. And if you can't plug a 0 into the denominator, the only way to get an output of 0 is if the numerator can be 0. But in this equation, 1 is the numerator, so the output can never be 0. Back in Chapter 2, we talked about transformations on graphs, how we could move a graph up, down, left, right. Well, remember that when you had a function and you added a number to it, you move the graph up. If you subtracted a number from it, it went down. If you added a number to the input of the function, it moved the graph to the left. And if you subtracted from the input, it moved the graph to the right. So if you think about r of x equals 2 over x minus 3 as a transformation on the graph 1 over x, you'll notice that the graph went to the right 3 and it got stretched vertically. Not that I'm worried so much about that, because stretching vertically doesn't change where the asymptotes are. But if the original asymptotes of 1 over x were the x and y axis, but now I move the graph 3 to the right, that means my new vertical axis, let's make that look a little bit nicer, my new vertical asymptote is going to be at 3. So now my asymptotes are x equals 3 and y equals 0. Moving a graph left or right does not change the horizontal asymptote. So what is the graph going to look like? It's going to look like this. And that's all without my calculator, just by memorizing the parent function 1 over x and determining how the graph has been transformed. In this second function, 3x plus 5 over x plus 2, it would be really awesome if this equation were set up in the same format as the last one, so it would be easy to tell what the transformations are going to be. Well, I claim to you we can rewrite it. What we're going to do to rewrite it is we're going to perform longhand polynomial division, because fractions are just division problems anyway. So how many times does x plus 2 go into 3x plus 5? Well, it goes in 3 times. So then I multiply the divisor by 3, and then I subtract, and I find out that the remainder is negative 1. So the new function is actually 3 minus 1 over x plus 2. I wrote the minus out in front instead of writing plus a negative. Well, now I know how this graph has been transformed. First, this moves the graph up 3. This moves the graph to the left 2. This reflects it over the x-axis. So now if I'm trying to figure out where the asymptotes are, the asymptotes must be at 3, -2, and then instead of being in the upper right-hand corner and the lower left-hand corner, the graph must be here and here. And at least that gives me a general sketch of what's going on. Now, can we do this with all rational functions and rewrite it so that its parent graph is back to 1 over x? No, we can't always do that. So we have other ways of determining the asymptotes. Let's look at a more complicated rational function. R of x is equal to 2x squared minus 4x plus 5 over x squared minus 2x plus 1. Now I realize that you can graph this on your calculator with no problem. What I want to do is I want to use this section of the book to find important information about rational functions, such as the vertical and horizontal asymptotes. And I also want to find out how to find the x and y intercepts, which can also be very useful information. Now, if you can factor, you do. And in this case, only the denominator is going to factor. If you don't believe me, if you graph the numerator in the calculator, you can only factor a quadratic if it hits the x-axis and the solutions are rational numbers. Well, the numerator doesn't even hit the x-axis. So the denominator, it factors into x minus 1 squared. To find the vertical asymptotes of any rational function, you take the denominator and set it equal to 0 and solve. Well, we're going to find out that the vertical asymptote is x equals 1. So that means if I drew a little graph here, there would be a vertical asymptote there. Well, how about a horizontal asymptote? Well, one way of finding the horizontal asymptote that is a precursor to some stuff we'll do in calculus is if you take the biggest exponent of x and you divide every term by that biggest exponent. So the biggest exponent of x is x squared. So I'm going to divide everything by x squared. And then I'm going to simplify. And I get 2 minus 4 over x plus 5 over x squared in the numerator. And I get 1 minus 2 over x plus 1 over x squared in the denominator. And then you ask yourself, what happens to each one of these terms as x gets infinitely large or small? In other words, what happens as x goes to infinity? Well, the 2 and the 1, nothing happens to them because I can't change x because there's no x. But the 4 other fractions have x's in the denominator. The larger the denominator of a fraction, the smaller the output of the fraction. So the bigger x is, these all go to 0. And they basically go away, so you end up finding out that the horizontal asymptote is 2. Alright, so there must be a horizontal asymptote here. Next, let's find the, well, we're not going to find the x-intercepts. We won't worry about that yet. We'll come back to that another time. Now, if you graph these on your calculator, you kind of see that you see that the graph basically looks like this, where it's getting closer to the green line. I know the way I drew it makes it look like it crosses the green line, but you're going to pretend like it doesn't. And then it gets closer and closer to the blue dashed line. But I'll show you another way of finding a horizontal asymptote in a moment. All right. You can graph this in your calculator if you want to look at what it looks like, but you don't have to. We're just going to find the asymptotes. And one of the things that I said is you can find the vertical asymptote by setting the denominator equal to 0. Well, you have a couple ways of doing this. One is to factor the denominator. The other is to just graph the quadratic in your calculator and find where it hits the x-axis. So if you graph this in your calculator, just the denominator, you'll find out it hits the x-axis at 1/2 and -2. So those must be my vertical asymptotes. Here's the other way of finding a horizontal asymptote. I claim to you that the horizontal asymptote is 3/2. The reason is because there are 3 things that can happen when you go to find a horizontal asymptote. Try that again. There we go. Here's one thing that can happen. If you have a function where the biggest exponent of x in the numerator and denominator of a fraction are the same. So notice that x squared is the biggest exponent in the numerator, x squared is the biggest exponent in the denominator. Then the horizontal asymptote must be a ratio of the coefficients of those terms. However, if the bigger exponent of x, let's do this, is in the denominator of the fraction. So in this one, x squared is the biggest exponent, but it only occurs in the denominator. Then the horizontal asymptote must be 0. And then there's a third thing that can happen. What if the bigger exponent of x is in the numerator? If the bigger exponent of x is in the numerator, we say that the horizontal asymptote does not exist. Or you can use this. Either way works. So now if you look back up here, it kind of makes sense that the horizontal asymptote would be at 3/2. If you graph this on your calculator, though, one of the things you'll notice is that the graph part that's in the middle does actually pass through the horizontal asymptote. That's because when you have multiple parts of a graph, so sometimes a discontinuous graph can be in 2 parts or 3 parts or 4 parts, it can often happen that part of the graph actually asymptote. However, in a rational function, it will never cross the vertical asymptote, even if it can sometimes cross the horizontal asymptote. Sometimes when dealing with rational expressions, it helps if you can try to factor everything, if you can. We ran across a problem earlier where you could not factor the numerator, and that's all right. So in this polynomial or rational function, 2x squared plus 7x minus 4 over x squared plus x minus 2, in order to find the vertical asymptote, I need to factor the denominator. Well, the denominator factors into x plus 2x minus 1. Or you can just graph it and find where the denominator hits the x-axis if all you do is graph that portion of it. That'll tell you the vertical asymptotes. My vertical asymptotes are at -2 and +1. The horizontal asymptote, I look for the biggest exponent of x in the numerator and denominator. Luckily, they're the same. So the horizontal asymptote must be a ratio of the coefficients in front of those terms. Well, now I'm going to go and I'm going to find 2 additional things. Let's see, I have -2 and 1. That means my graph will be in 3 parts. And then here's my horizontal asymptote. The other things that I'm going to find are the x and y intercepts because they can often be very useful information. To find the x-intercept, all you have to do is take the numerator, set it equal to 0, and solve. Now the reason we can do that is because to find an x-intercept, you make the output 0. So if I make y 0, it's really a fraction 0/1. So when you cross multiply, the denominator just goes away because you're multiplying the denominator by 0. So you're left with 0 equals the numerator. Again, you have two choices. You can factor this or you can graph it. I'm going to go through the factoring process to do a reminder of how it works. When the leading coefficient of a quadratic is something bigger than 1, you multiply the first and last terms, and then you write down all the factors that multiply to give you that. Only one of those pairs, when you add them, is going to give you 7, because you want the pair of numbers to add up to the middle term. So I'm going to rewrite this as 2x squared minus 1x plus 8x minus 4. And then we're going to do something called factor by grouping. You group the first two terms together, you group the last two terms together. And then you factor out the greatest common factor from each of the groups. The greatest common factor in the first group is x. The greatest common factor in the second group is 4. So this must factor into x plus 4, 2x minus 1. So the x-intercepts are at negative 4 and 1/2. Now, will there always be two x-intercepts? No, there could be one x-intercept. There could be no x-intercepts. It just kind of depends. So I do know the graph is going to hit the x-axis here and here. How about the y-intercept? Well, the y-intercept you're going to find by replacing all the x's with zeros in the original equation. Well, oops, sorry about that. Let's look back at the original equation. If I replace all the x's with zeros, these all go away, and I'm left with negative 4 over negative 2. My two-finger scroll up, not working. So negative 4 over negative 2 is 2. That means that on my graph here, I must hit here. Well, if I graph this on my calculator, I'm going to end up seeing something that looks like this. This does not cross either asymptote. This middle portion does cross the horizontal asymptote, but that's okay. And then there's a portion up here that doesn't cross either asymptote. So it gives you kind of a brief understanding of what the graph's going to look like. But again, I realize you can do it on your calculator. However, what I want you to be able to do is I want you to be able to find algebraically the vertical asymptote, the horizontal asymptote, the x-intercept, and the y-intercept.